So we already covered actually the Euler-Lagrange equation, but here you can just find the slides about the equation. So the equation uses the Hamilton principle of last action. So the motion of autonomous or conservative mechanical system with kinetic energy and potential energy tries to minimize the function of Lagrangian. And because of that, you can actually easily derive from the Hamilton principle the equation. For the non-conservative system, it will look like this. So here, the right side was equal to 0. Here it's the external forces and torques that could be applied to a system. And basically, the derivation of equation of motion will be pretty much the same as in your first practice task or the second practice task, but now we're going to use the components from the linear algebra, and matrix C actually is nothing else as something that can be computed if you do know already matrix M. If you do know matrix M, matrix C could be computed out of it, actually. So let's assume that we have a robot. How can we compute the kinetic energy? We need to, of the whole system, we need to sum the kinetic energy of each of them, of each of the links. How can we compute the kinetic energy of one link? We need to multiply the twist transpose times the inertia, just like we just derived. How to compute twist? One way to do this using this notation, if you do know the h's, or we can, even simpler, we can use Jacobian. So at the previous lesson, we derived Jacobian not only for the whole robot, but for each link. Jacobian of the first, the second, for all of them. So the kinetic energy, for example, for the second body will be Jacobian of the second body times the vector of velocities, joint velocities, and it will be the twist for the body. And since we know that the twist is the constant for all the points, so this will be the case. The only thing that we need to do is to express it in the principal frame, such as the tensor of inertia has only components on the main diagonal. Those components can be easily be calculated for basic geometry shapes such as brick, cylinder, I don't know, ellipsoid. As for the something complex, you can find it from your CAD software, because software is able to calculate it for the principal frame, and you can just put it inside, and the MATLAB do the same basically. So if you open a brick solid, you can find the inertia derived and the three components for the moments of inertia. So basically, since we talk about the rigid body dynamics with the constant mass and constant inertia, those will be the constant value. Here you can see the equation for the kinetic energy. Kinetic energy of a body, it's like 1/2 times the vector of the velocities. Here it will be, could be angular velocity or linear velocity, it doesn't matter actually. And matrix M computed as Jacobian transpose, adjoint transpose inertia, adjoint Jacobian. Once again, adjoint is needed to express it in the principal frame. M is the inertia matrix, is the first matrix in the equation of motion, and the inertia matrix for whole robot will be just a sum of inertia matrix of each link. As for the potential energy, pretty much the same, mgh, but h now can be computed out of h, just homogeneous transformation matrix from here. You just need to grab the proper component out of there, and the potential energy is just the sum of potential energy of each link. Now if we'll try to compute the whole equation, we already actually know m. M is just the sum of m of each link. The only thing that as we need to do is to calculate the matrix C and J. J is the gravity. It will be just the partial derivative for the potential energy, and that's it. The only thing that actually need to be computed is C matrix. So here you can see the Lagrangian. So the Lagrangian is the difference between the kinetic energy and potential energy. The dimension of Q is the number of joints. For example, if you have a robot with 3 joints, then it will be the dimension of Q. If your robot has 6 joints, the dimension of Q will be 6. So it depends on the topology of your robot. Then we can calculate the partial derivative of Lagrangian in respect of Q dot. It means that we need to just get rid of Q dot I, and you'll be left with just Q dot J. I and J, you have a matrix, and Ij just components from this matrix. And from here you can compute the full time derivative. So it will be the derivative of a product. This is why here now it will be Q double dot plus M dot Q dot. It is for the first term of the Euler-Lagrange equation. As for the second term, we need to take the same Lagrangian and take the partial derivative with the Q, and you will be left with this part. So we can continue actually the whole derivation. It takes a while to understand all these components and why. So from here maybe it's not exactly clear how to derive it, and it's not my point here. My point here is that actually we will continue all this derivation, and I encourage you to read about in this book of Kevin Lynch. We will get the following. So for the first component, m double dot m q double dot. So this is the component. Delta v q goes from here, but in the middle, something in the middle, we denoted with the Christoffel symbol with the capital gamma, and it equals to this stuff. And you can see that capital gamma times q dot is nothing else as the Coriolis vector, and we can compute it if we do know the matrix M. So automatically out of there, and we do not need to compute it independently. If you do know the matrix M, it will be much easier to compute this equation. So basically, in my example, I'm taking advantage of this idea. here you already are provided with this example, but let me just give you additional instructions. So this robot is able to rotate around z-axis, the first link, and as for the second and the third, those are able to rotate around the x-axis. So since we do know the direction of the rotation, we are able to write the unit vectors for angular velocities. So 0, 0, 1 for z, 1, 0, 0 for the x, for the second link and for the third. Then the position of joints. So we already covered that, but I'll just be very quick about it. So the position of the joints, where is the joint in very initial state. Then we need to use this skew symmetric representation to compute the vector v. So v equal to minus angular velocity in skew symmetric form times r. Right here, as the result, you can see this v's, and this is the component of twist. So here you can see an example of twist for the third body. So here are the initial homogeneous transformation matrices for the all the center of masses and the end effector. This is the Rodriguez formula, the H Brocket exponential formula for the kinematic, for the direct kinematics Jacobians, and we need all of this actually to compute m's. So here we can see m, m1, m2, m3, and the total m is just the sum of m1, m2, m3. So here we had the equation for the m for just one link I. Its matrix will be equal to the Jacobian, the corresponding Jacobian transpose times adjoint times inertia tensor adjoint Jacobian, and this is exactly that you can see right here. So the corresponding Jacobian adjoint for the center of mass. So it's actually the principal frame. Principal frame, it's the one where you have the center of mass transpose. So that with the prime, it is transpose. I3, it is the tensor of inertia. So here you can see that it's 6 by 6, and we have components for the moments of inertia, x, y, and z, and m3, m3, m3. Another adjoint with angular with the Jacobian. Is it clear? So we computed m, and you can see how great it is symbolically. Then we computed the potential energy, and it's just the potential energy of all the bodies. How do we compute potential energy? It's the multiplication of the mass, gravity component, J, and the height. The height can be taken from here. Just make sure that you chosen the right coordinate. Is it y or z? Depends on your choice of coordinate representation. So, and then you can see that in order to get c, I have this function get c, and it's right here. So get c, it is the function that computes the value for the vector c automatically if we have matrix M, the vector of positions q, and dq. dq is the vector of velocities. So This is the Q and dq. Pretty much that's it. Now you can find here m, c, and gravity. So you can just copy it and put it to your dynamics, and actually can do the same for your second practice task. You can just check yourself. So for any kind of robot, if you do have a prismatic joint, it means that your angular velocity equal to zeros, and in order to compute linear velocity, you don't need to multiply the angular velocity with r. It will be just 0, 1, 1 for example for z, for x, or 0, 0, 1 for the z. And so, for example, you have this kind of robot. So, for example, you have this prismatic joint. This is your frame. This is z, y, and x. What is the direction of the prismatic joint? Y, yeah, and this is why your v will be 0, 1, 0. Yeah.
We can do it just with our sites.
Yeah,
like
just inspection. And pretty much that's it.